Video for investigation 7B, which is called Doppler radar. And I really like this investigation. This has been an investigation that the AMS has had on its docket pretty much the entire time I've taught this course over many, many years. And it's been kind of fun for me to see how the AMS has evolved this particular investigation to integrate better graphics. And so this is another example that we're going to be seeing for me where the graphics have actually improved over previous incarnations of the Doppler radar investigation. Now you may notice that I actually have my browser window kind of down a little bit from the top of my screen. And that is because question 1 is showing if I have it all the way at the top of my screen. And I have my key on my investigation manual because I shade everything in terms of the keys. So the AMS, that actually does keep an eye on my videos from time to time, really doesn't like it when I show answers to investigation questions. And so I'm being a good person for the AMS and not showing the keys. So that's what the offset is here. And I think it'll probably be about the only time that we have this offset this session. So why don't we just kind of get that out of the way and start our slideshow and talk about Doppler radar. So there it is. And so this is one of these examples where the AMS has kind of just made a graphic a little prettier than it used to be. And it is this top graphic right here, which is really just a depiction of a Doppler radar on the stand. So when you see a Doppler radar, and you can actually just do a web search for Doppler radar, take a look at a couple of images, and what you'll see is that Doppler radar is ground-based, and it is typically located on a fairly tall pedestal. And what you'll see at the top of that pedestal is a big white sphere that looks like a golf ball or a volleyball. It's huge. And it's actually a shelter for the Doppler radar, which is located inside there. So the Doppler radar is located inside the shelter, and it just kind of whirls around in a circle, sending out pulses of microwave energy that is then scattered back to the radar, actually in all directions, by droplets and crystals in the clouds. And that's how we actually detect precipitation in clouds. And then based on the size and the density of those objects, we can determine not only whether it's going to be falling from the cloud, but then get a sense of the actual precipitation rate. Now, when we look at radar, and we've already taken a look at radar in our class, what we've looked at is base reflectivity radar. And base reflectivity Doppler radar is pretty much what I just described, where the radar sends out pulses of microwave energy that is then scattered back, and then we can figure out not only whether or not precipitation is falling from the clouds, but the rate at which that precipitation is falling. So when we take, and this is what we see on TV and typically on the internet, this is what everybody's used to. And we're going to take a look at a base reflectivity image later on in this video. But base reflectivity is pretty much what the public has been trained to look at and to understand. Now, Doppler radar was actually developed and actually went operational in the mid-1980s, not just to look at base reflectivity, but to get a sense of motion at cloud level so we could identify rotation. And so what we see here in figure 7B1A is a depiction of a rotating cloud, and this would be the mesocyclone of a supercell thunderstorm. This is typically where we get our rotation. You can see we've got counterclockwise rotation and a nice depiction of a thunderstorm. So what the Doppler radar does when it is in what we call velocity mode is it senses motion both toward and away from the radar. And so let me just put up part B of this figure. And so this is looking down on the Doppler radar from above. So the radar is actually located where we have this little circle with the X in it. This little streamline right here is just depicting the motion of the radar inside the shelter, so it's clockwise in this example, and sending out these pulses of microwave energy. And so this basically just shows you when the pulse is coming out in position 1, 2, 3, 4, and 5. And here is our rotating thunderstorm. Again, this is actually what meteorologists refer to as a mesocyclone. Almost always, but not always, but almost always rotates counterclockwise. And what you can see from above is that the motion of the mesocyclone ultimately leads to some parts of the movement being toward the radar and other parts of the motion being away from the radar. So you can see that in two of the positions, the motion is directly toward and away from the radar. And then you can see in these other two positions, 2 and 4, that we have a component of the motion that is toward and a component of the motion that is away. So the motion doesn't have to be just purely toward or away, but what Doppler radar does is it senses that component of the motion is toward or away to the radar. Now, the way the Doppler radar works and is able to actually sense this motion toward and away is it uses the fact that the energy being emitted by the radar has a wavelength and a frequency. All electromagnetic energy, and this includes microwave energy, moves roughly at the speed of light. And this energy has a wave-like motion to it as it's moving along at this very fast speed. And frequency is just a measure of how many of those waves moves past a point in a second, basically. So when the motion is toward the radar, what that motion does is it actually compresses the wave that's moving toward the motion a little bit so that the wavelength gets a little bit smaller and the frequency gets a little bit higher. So that scattered energy that comes back to the radar will have a slightly higher frequency, and the Doppler radar will actually measure that as motion toward the radar. If the motion is away from the radar, what happens is that not only is the beam moving out from the radar, but the motion being away from the radar just stretches that wave out a tiny bit, even though it's being scattered back to the radar. So the wavelength gets a little bit longer, the frequency gets a little bit lower. So basically, we get an upshift in frequency when the motion is toward the radar, and a downshift in frequency when the motion is away from the radar. Now, the Doppler principle was developed to actually assess changes in the frequency of sound waves as objects are moving toward or away from a person. So if you are standing outside, and if you're in Bowling Green, for example, and you are kind of trying to cross Worcester Street and a train is coming, you'll actually hear as the train is moving down the tracks towards you on Worcester Street, you'll actually hear not only it getting louder, but you actually hear the frequency of the sound going up as well. The pitch goes up. And then you're sitting there waiting or standing there waiting for the train to go by. And when the train finally is done and it's moving away from you, not only will the intensity of that sound go down, the loudness go down, but the pitch or the frequency will go down as well. So what happens as the train is coming towards you is that the Doppler effect causes the sound waves to be compressed, the frequency to go up, and the pitch to go up. And when the train is moving away from you, the Doppler effect basically causes the sound wave to be stretched out, the frequency to go down, and the pitch to go down. So basically, we're using that same principle of sound waves that Doppler principle was developed for and applying it to microwaves with radar. Now let's take the bottom part of this figure, and what I want to do now is just follow the instructions that the AMS gives you and to shade in this circle just a little bit. And what we're going to do, because this is what we see when we're looking at Doppler radar in velocity mode, is when the motion is toward the radar, it's going to be shaded green. And when the motion is away from the radar, it's going to be shaded red. So if you take a look at the upper part of our circle, so basically the upper semicircle, you'll see that the motion is either directly toward the radar or there is a component of the motion that is toward the radar. And just following the instructions, you're going to shade in this part green. So you're going to shade in the upper semicircle green. Now for the lower semicircle, you're going to have motion that is either directly away from the radar or partially away from the radar. And you're going to shade the lower semicircle red, because this is what we're going to see again when we're taking a look at Doppler radar in velocity mode. Now the example that we're going to be given in this particular investigation does not really show a sharp transition between motion toward and away from the radar, but often what you'll see on Doppler radar when you basically have this zero Doppler line. So basically you go from motion being toward the radar to away from the radar, there is this line where the motion is neither toward nor away. So if you take a look at this particular example in position 3, what you see is that even though there's motion, the motion is perfectly tangent to the radar. It's neither toward nor away. We have motion, but it is tangent to the radar. So when you've got a zero Doppler speed, what you're going to see, and again, we're not going to see it in the example for this particular investigation, but what you'll typically see is a transition zone that is gray. So you'll go from motion toward to motion away, and where you have that transition from toward to away, you'll have typically a gray line. It's fairly thin. Sometimes it's kind of sinuous, but it's going to be thin and it's going to be gray, and that's where you have zero Doppler velocity, where there's motion, but it's neither toward nor away from the radar. All right, now what we're going to take a look at for the rest of this video and for the rest of the investigation is an example of a tornadic storm, a supercell, that came through Alta Vista, Kansas, which is in northeast Kansas, on March 13th, 2024. Now what I have here is the surface map for the US at 0Z on March 14th, 2024. So the tornado actually came through Alta Vista right around 0Z, give or take a couple of minutes. So this is the closest I was able to find. What I'm going to do is I'm going to just put a circle right here where Alta Vista is located. So it's a big circle. It covers a chunk of northeast Kansas. But Alta Vista is in northeast Kansas. This is where it's located. And this is where this tornadic storm occurred. And you'll see that Alta Vista is located just to the north of a stationary front that extends from a fairly vigorous low pressure system on this particular date at this particular time. And there's a lot going on here involving wind shear that we'll talk about when we get to investigation 11B, but we're not going to talk about it today. Just suffice it to say that the conditions were obviously conducive for a fairly major tornado to develop, and one did. So this is just the setup for the Alta Vista tornado. You're not given this map in the investigation. I just wanted to put it on here so you can just get an idea where Alta Vista is actually located. Now, what the investigation does do is it gives really, really nice images of the tornadic supercell thunderstorm in base reflectivity mode. By the way, the Topeka, Kansas Doppler radar is located right where I have my cursor, so you can see this fairly large gray circle, and that red dot in the middle is where the Topeka Doppler radar is located. And you can kind of see these radials that we have these sort of pixelated radials extending from the radar. So the resolution of this particular Doppler radar image is not the best in the world. There are some incredibly high resolution Doppler radar images out there where you don't see any of this pixelation at all, and it's much smoother looking. But what you can see is really, really interesting is that the rotation, the mesocyclone, in fact, is located right where I'm circling with my cursor. The main tower of the thunderstorm is up here, and you can see my cursor a little bit bigger, hopefully. It's not getting big for me. There it is. It's right here. This is where the main cell is located. And typically you get your largest hail and your heaviest rain falling out of the main cell. Now what the mesocyclone does is, with its counterclockwise rotation, it kind of wraps this cloud level air around the mesocyclone and forms what we refer to as a hook echo. So a hook echo is basically this wrapping around of this cloud level air, this cloud and precipitation around the mesocyclone. And when you have a really high resolution image, what you'll see is typically a purple ball right here, very, very high reflectivities. And this is referred to as the debris ball. So the debris ball is literally where the tornado is located. It's located at the tip of the hook. And with the debris ball, you've got flying shingles and pieces of house and trees and cows and you name it. That's what's flying around in the debris ball. So we don't have the highest resolution image here. So the debris ball, it does show up, but it doesn't show up as a nice bright purple, which we often see in our highest resolution images. So this is base reflectivity. Now, just a cautionary note. Not every tornadic situation will show a beautiful hook like we have in this example. Sometimes the hook is absent. The tornado will be part of a larger shield of thunderstorms along a front or something like that. And so one of the problems with just using base reflectivity to try and forecast tornadoes is that A, sometimes you don't get a hook echo, so you miss it. And B, you typically only get the hook echo right around the time when the tornado is actually touching down. So wouldn't it be nice if we actually were able to identify rotation at cloud level 30, 45 minutes before the touchdown of a tornado so that we could actually give the public lots of warning so they could get to safety? And the answer is, yeah, it would be great, and now we can do it. Because when we take a look at Doppler radar in velocity mode, what we're actually able to do is what I just said, which is to identify rotation at cloud level, typically several minutes, maybe even 30, 45 minutes before a tornado touches down, so that when we see this rotation, the National Weather Service, the local National Weather Service office can issue a tornado warning, the sirens go off, and people can actually get to safety before there's a touchdown. And in fact, with Doppler radar, in the last 40 years or so, the number of tornado fatalities in the United States has really plummeted because of this increased lead time for people to actually get out of harm's way when there's a tornadic situation. So let's take a look at the same exact Doppler radar situation, only when we're in velocity mode now instead of base reflectivity. And here it is. Looks completely different than base reflectivity. I would venture that the vast majority of us in class have not actually seen a base velocity image, but this is what it looks like. So let's set it up for you. First of all, here is the Topeka Doppler radar. So here's our gray circle, and here is our little red dot with the Doppler radar right in the middle. Now, before we talk about the colors here, I'm going to move right over to the legend, the scale on the left-hand side of our velocity image. So these numbers are velocities in knots. So I'm going to just start here at 0, and you'll notice the gray, by the way, for the 0 Doppler speed that I talked about a slide ago. So here is our 0 Doppler speed. I'm going to go to the negative numbers. The negatives indicate speed toward the radar. So we're going to move our way through the darker greens to the brighter greens. And for really, really fast speeds, we're going to move through light into dark blue. And you can see at this point that we're getting speeds upwards of 80, 90, maybe even 100 knots in extreme cases. So 100 knots is about 115 miles per hour straight at the radar. Now, if we go back to our zero Doppler speed and start moving our way through the reds, from the dark reds through the light reds into the salmons and then the oranges, you can see now that we have positive numbers, and these are speeds away from the radar. So speeds away from the radar, and again, the scale goes way, way up to like 125 knots. It's very unusual to see us get to the top of the scale here. If we do, we're talking about a very severe EF4, EF5 situation. But here's our Alta Vista tornado example. So here is our radar. By the way, here's Alta Vista. And this particular tornado has already done its damage for Alta Vista. It's actually moved off of Alta Vista, and it's actually moving towards Topeka at this point. Now, here is this little green oval, or it's kind of like a bean shape right here, and this is our motion toward the radar. And here's this area of salmon color indicating motion away from the radar. And so what you can see is this phase shift in velocities, in direction over a very small distance. And when you see this, meteorologists refer to this as a tornadic vortex signature, or a TVS. And so when you see a TVS, this indicates rotation, and this is when the National Weather Service will put out the tornado warning. Now, if we just move a little bit closer to Topeka, what you'll see is a large area of motion toward the radar and a large area of motion away from the radar. So this is not tornadic. This is just the general motion of the air at cloud level around Topeka. And you'll see that here's our gray zero velocity line, by the way. So there is this general motion basically toward the radar, and you'll notice that we abruptly shift from toward to away. The motion hasn't changed. It's just that the motion here was upstream of the radar, and now it's downwind of the radar. So the color just changes as soon as this motion, which is all in the same direction, crosses that line. So this is just our general motion versus our very obvious phase shift in TVS just to the northeast of Alta Vista. Now what I'm going to do is I'm going to just break out this velocity image in the next slide. I'm going to put some arrows on it so you can just get a sense of the motion and how it is we actually determine the rotation caused by this tornadic signature. So this is just the same velocity image as I had on the previous slide. But what we're going to do here is I'm going to put on a couple of arrows just to show you motion, first of all, around the radar, and then in the tornadic vortex signature. And I'm going to actually put a little flywheel, a little asterisk in here, just to give you a sense of how this phase shift leads to rotation. So I'm going to click a couple of times. Here's arrow number 1. This is the motion in the vicinity of the Topeka radar. So in the green area, this is motion toward the radar. And you'll see that the motion is anywhere from about 20 to 40 knots. Now, once this motion crosses the radar, the motion goes from being toward the radar to immediately away from the radar. It's the same wind, same direction both on both sides of the radar, but it just goes from being toward to away. So you can see that this is the general motion of the air in the vicinity of the Topeka Doppler radar. Now you'll notice that as we move towards this tornadic vortex signature, we have this area of really, really strong winds right here, which is again away from the radar. So what's happening here is that as the beam from the radar moves off, it's moving at an angle, and basically it's intersecting cloud that's at higher and higher altitudes. And as you get higher above the ground, the speed increases, and you're actually seeing that increased speed signature right here. But it's still motion away from the cloud. It's just increasingly fast. Now let's talk about the motion actually caused by the tornadic vortex signature itself. And I'm going to start with the motion here in our green sort of bean-shaped area. And I'm going to put an arrow indicating that this is toward the radar. Now just notice this core of very dark blue right here. So this is toward the radar at about 80, 85 knots. Really, really fast motion. There it is. And then I'm going to take a look at the salmon area, this little area right here. It's a little bit smaller than the area toward, but it's still very, very intense, more like 60 to 70 knots. But it's away from the radar. I'm going to put another arrow here just indicating motion away from the radar. Now notice that these two arrows are directly toward and away from the radar, because that's all we're seeing here is motion toward and away. Now what I'm going to do is I'm going to put a white asterisk right in between these two arrows to basically just indicate a pinwheel. Think of like a pinwheel on a toy that you can blow on and make spin around. So here is my little pinwheel. Now the bottom of the pinwheel is being pushed toward the radar. The top of the pinwheel is being pushed away from the radar. So basically you're blowing the top of the pinwheel in this direction, and you're blowing the bottom of the pinwheel in an opposite direction. And as a result of that, and just take a look at my cursor, it's going to lead the spin. And so it is this spin, it is this rotation that is imparted to the air by this couplet that actually leads to the rotation and allows the National Weather Service to identify this tornadic vortex signature and then to issue the tornado warning to warn the public. So you can't do this with Doppler radar and base reflectivity. You can only do this with Doppler radar in velocity mode. And so that's why Doppler radar in velocity mode is so important. And it's really a pity that this is really not shown to the public on TV very often at all, because I do think that the public can learn how to use this and understand it. But TV meteorologists in general just don't do it. So when you're looking at radar and you're doing this on your own, particularly if you're interested in severe weather, look for these radars that are in velocity mode. Go to the National Weather Service and take a look at National Weather Service Doppler radar and take a look at it in velocity mode, and you'll be able to see examples of this. Now again, if you're just taking a look at a general rain, snow example, a large-scale rain or snow example, you'll see what we have up here when we're just showing motion in the vicinity of the Doppler radar. And that's good, and it's good training, so that when you do come across an example of severe weather that is tornadic, that just show rotation, you know what to look for. Okay, I think that's pretty much everything I'm going to say about Doppler radar in this video. So that's it, that's all. If you have any questions about anything I've said here about Doppler radar, by all means, feel free to post a question to the discussion board or ask me live during my office hours on Zoom. But that's it, that's all. I'm going to end this now, upload it to YouTube, and you'll see an announcement when it's ready for you to view.